Good morning, viewers. Welcome back to channel enginiusmechtech. Today we are starting our chapter number 23, name cutting tool technology. I hope previous lectures are very good to you, and now I am trying my best to improve my teaching lectures and also to deliver my main point to you in a good way. I hope you are doing well. So we start our chapter. First of all, we use the terms what is cutting tool technology. How we in this chapter our target is to achieve the tool life and how to select tool material, what is the importance of tool geometry, and what are the cutting fluids and how cutting fluids affect the life of tool. Cutting tool technology, there are two principal aspects. Number one is tool material, number two is tool geometry. It's mean that how tool material will affect the cutting machining operations and tool life, and how tool geometry will affect the operations and also the life of the tool. There are basically there are three modes of tool failure. Number one is fracture failure, number two is temperature failure, and number three is gradual wear. What is fracture failure? Cutting force become excessive or dynamic, leading to brittle fracture. It is actually the breaking of some material and cracking of some metal and so on. All the things are the fracture. As it is clear from the name that cutting failure is what? Temperature failure. Cutting temperature is too high for the tool material. Gradual wear of cutting tool. But what is the desired failure? As you know, after some time the tool must be failed. But what is the desired failure? The gradual wear is the desired failure because it has the longest life. We will see in the next slides. This is the thing. Preferred mode of tool failure is gradual wear. Why? Fracture and temperature failures are premature failures. But the gradual wear is preferred because it leads to the longest possible use of the tool. Why? Because it has the longest life, as it is our desiredness, it is our desire. Gradual wear occurs at two locations. What are these two locations? These are on a tool, crater wear and flank wear. Crater wear occur on the top break face and the flank wear occurs on the flank, the side of the tool. You can be more clear by the picture. Yes, that's the and this is some kind of cutting tool and this is the cutting edge. And this is the crater wear. As we feed inside in this way tool, this is the area where the chips of the machine of the work tool strikes. This is the crater wear. This is irregular in shape, and this is the flank wear. This is the direct contact with the work part. So this is the depth of cut, and this is due to the feed, and this part is due to crater wear, and this is the flank wear width, etc. These are all the terminologies related to the cutting tool failure. Yes, this is the real picture. This is the crater wear. This is the flank wear on the side of the tool. Break in period. This is the this is a graph showing the tool flank wear related to the cutting time. Initially, the wear is more because it's a new, and we will check out. We will be noticed some rapid wears, but after the time increase the wear is reduced, but at the final stage it's again the failure is high with respect to cutting time. I am so sorry, today my voice is a little bit low due to some kind of rashness in my throat. This is due to the climate change in our area. So we will move. You may notice my climate change video in the uh, in my channel. So we move toward our lecture. This is the effect of cutting speed on the tool flank wear. This is different cutting speeds. This is for the this is the flank wear for the velocity 160. This is the wear for the 130, and this is the for less speed. For less speed, it cutting time is more cutting times. So the life is high here. This is the natural log plot of the cutting speed. This is something a log graph of the above thing. Taylor tool life equation. This relationship is credited to F. W. Taylor. The Taylor era is approximately near to 1900. The equation of the Taylors is given by V t power n is equal to c, where v is the cutting speed, t is the tool life, and n and c are the parameters that depend on feed. Depth of cut, work material, and the life tool life criterion is used. N is the slope of the plot here, and c is the intercept on the speed axis. That is, I think, the y speed, sorry, y intercept. The tool life criterion in a production. What are the criteria for tool life? Complete failure of cutting edges. It may be complete edges. Visual inspection of flank wear or crater failure by the machine operator. Fingernail test can be done for tool life checking. Changes in the sound emitted from operation. These things are these things can be measured by only experience, not by any tool. Chips become ribbony and stringy and difficult to dispose of. Degradation of surface finish, increased power, workpiece count, and cumulative cutting time. These are all the factors that can tell us that is the tool is better for further use or the tool has been failed. These things are very much important. The tool materials. Tool failure modes identify the important properties that a tool material should possess. What are these properties? Number one is toughness. Toughness is to avoid fracture failure. Hot hardness is ability to retain hardness at the high temperatures, because this is the cutting operation. There must be friction in cutting operation. That when we apply force, there is high friction. Then metal heats up. These are all the things. And the final is wear resistance. Hardness is the most important property to resist the abrasive wear. Typical hot hardness relationship for the selected tools materials, plain carbon steels, that are the some things. This is the hardness, that is Rockwell hardness, and this is the temperature. As you can see from the graph, that if we increase the temperature, the hardness is reduced. That is in the same case for the plain carbon steels, high carbon steels, cemented carbides, cast cobalt alloys, ceramics. These are all the things, but in the case of metals, the change is high. For the less temperatures, the hardness is reduced to high, but for the ceramics and carbides, the temperature is very much high, but hardness is a little bit low. So these are the effects that how material will change its hardness regarding temperature. These are some typical values of N and C's that are used in Taylor tool life equations. Uh, N is 0.125 for non-steel work and 0.125 for the steel work. 0.25 for cemented carbides, in the case of cemented carbides, non-steel work, and in steel work 0.25. Ceramics, steel work 0.6. And the C is 120 for high-speed non-steel work, 70 steel work, high-speed steel. And if the tool is cemented carbide and the work is a non-steel, so 900, and steel work is 500. Ceramics, when the tool is made up of ceramics, the work is steel, so 3000. And these are all the things like these values are in meters per minute, and these are the feet per minutes. These are only just the conversion. High-speed steels (HSS) highly alloyed tool steels capable of maintaining hardnesses at elevated temperature better than high carbon and low alloy steels. These are high tough. These are the strongest of steels. One of the most important cutting tool materials. It is used as cutting tools, specially suited to application involving complicated tool geometry such as drills, taps, milling cutters, and projects. These are all the operators or the tools. We have previously discussed all the things. Two basic types are tungsten type designated T grades and molybdenum types designated M grades. High-speed steels composition. Typically alloying ingredients are tungstens, chromium and vanadium, carbon and cobalt in some grades. Typically composition grade T1 18% W, 4% carbon, chromium, 1% vanadium, and 0.9% of carbon. This is the, for example, the example. Cemented carbides, class of hard tool material based on tungsten carbide (WC), using powder metallurgy techniques with cobalt (CO) as the binder. Two basic types: non-steel cutting grades and only WC, tungsten carbide, cobalt. Steel cutting grades TIC and TAC added to WC. These are some kinds of compounds. Cemented carbides general properties. What are the properties? High compressive strength but low to moderate tensile strength. High hardness, good hardness, good wear resistance, high thermal conductivity, high elastic modulus 600 into 10 power 3 megapascals, and toughness lower than high speed steel. Non-steel cutting carbides edge used for non-ferrous metals and grey cast iron, properties determined by grain size and cobalt content. As grain size increase, hardness decrease, but toughness increase. As cobalt content increase, toughness improves, and wear resistance and hardness decreases. Steel cutting carbide grades used for low carbon, stainless, and other alloys. For those grades, TIC and or TAC are substituted for some of the tungsten carbides. Cermets, combination of titanium cobalt and titanium carbonitrates, etc., with the nickel and or molybdenum as binders. Some chemistries are more complex. Application: high speed finishing and semi finishing of steels, stainless steels, and cast irons. Higher speed and lower fields than cutting carbides create better finish achieved, often eliminated needing need for grinding. Cemented carbides insert coated with one or more thin layers of wear resistance material such as tungsten carbide, tungsten nitrides, or aluminum oxides. Coating applied by chemical vapor deposition or physical vapor deposition. Coating thickness is equal to 2.5 minus 13 micro blah blah. These are all the things. Application: cast iron and steels in turning and milling operation. Best application at high speeds where dynamic force and thermal shock are minimal. Ceramics. What are the ceramics? As you all know, these are some kind of non-metals, but stronger than the metals. Primarily fine-grained aluminum oxide pressed and sintered at high pressure and temperature into insert form with no binders. No binders are used in the insertion of aluminum oxide. Application is high-speed turning of cast iron and steel. Not recommending for heavy interrupted cuts due to low toughness, because toughness is low, so it cannot bear the multiple type of impact loading like. Also, aluminum oxide also widely used as an abrasive in grindings. Synthetic diamonds. These are very much important. Sintered polycrystalline diamonds (SPDs), fabricated by sintering very fine grained diamond crystals under high temperature and pressure into desired shape with little or no binder. Usually applied as coating, 0.5 mm thick or tungsten carbide cobalt inserts. And application: high speed machining of non-ferrous metals and abrasive non-metals such as fiberglass, graphites, and woodworkings. These are all the things where the synthetic diamonds are used, not for steel cutting. Cubic boron nitride is next to diamond. CBN is the hardest material known. Fabricated into cutting tools, inserts same as synthetic SPDs, synthetic polymer diamonds. Coating on cobalt inserts. Application: machining steels and nickel-based alloys. SPDs and CBN tools are expensive because it's used diamonds and cubic boron nitride. I'm sorry for using the shortcuts, using the abbreviations, so please don't mind. I have told you the names previously. The tool material must maybe these things: HSS, cemented carbides, cermets, coated carbides, ceramics, and cubic boron nitrides, and synthetic diamonds. Now coming to our tool geometry, what kind of geometry we need? There are two categories of the tools: single point tool, multiple cutting edges tools. Single used for turning, boring, shaping, planing, and multiple cutting is used for drilling, reaming, taping, milling, broaching, sawing. Single point tool geometry. This is the some things that is ECEA and cutting edge angle. Single cutting edge angle. This is the nose radius that must be given to reduce the resistance, to reduce the failure. This is the side rake angle. This is the back rake angle. These are all some kind of angles must be taken into account during the production of cutting tool. And this is single point. These are the same terminologies I have told you before. Now there are some kinds of inserts to improve the life of cutting tool. As you know, as you can see that if this insert is not here, the complete tool is wear out. But if we put some insert, this insert is of higher strength, of higher toughness than the tool. So we insert it, but why we cannot make completely with this part? Because these parts are too much expensive. Like if we use synthetic diamonds for cutting, it is very hard and tough, but it is so expensive also. So we use the cutting tool made up of HSS, and the insert is made up of some other material. These are some kind of clamps for insertion. These are the common insert shapes: circular, square, and these parallelogram, trapezoidals, triangles, and all the things, rhombus, etc. Twist drills, by the far most common cutting tools, are for the hole making, usually made up of high-speed steel. This is the taper shank, this is the shank, this is the neck, helix angle, fluid, point angle. These are some kind of important things. And this is the rag face, this is the cutting edge, and this is the chisel edge, this is the web edge, this is the margin. Twist drill operations. Rotation and feeding of drill bit results in relative motion between cutting edges and the workpiece to form the chips. Cutting speeds varies along cutting edge as a function of distance from axis of rotation. Relative velocity at drill point is zero, so no cutting takes place. A large thrust force is required to drive the drill forward into the hole. Twist drill operations problems. What are the basic problems? Chip removal, that how to remove the chips from the machine. Fluid must provide sufficient clearance to allow the chips to extract from the bottom. Uh, Friction makes matters worse. Rubbing between outside diameter and drill bit, newly formed hole, delivering of cutting edges. These are some kind of problems. Milling cutters. Principal types. How much type of milling cutters are? Plain milling cutter, form milling cutter, face milling cutter, end milling cutters. These are the kind of cutters. In the plain milling cutters, the cutting edges, and these are in the previous some kind of lecture I have discussed it a little bit. This is the relief angle, this is the clearance angle, this is the fillet, this is the cutting edge, and this is the rake angle. Palm milling cutter, peripheral milling cutter, in which the cutting edges have some spatial profile to be imparted on the work. Gear making, in which the form milling cutter is shaped into slots between adjacent gears. This is the face milling cutter, teeth cut on side and periphery of the cutter. End milling cutter looks like a drill bit but designed for applications are face milling, profile milling, and pocketing, cutting slots, engraving, surface contouring, and die shrinking. Cutting fluids are of most important thing to reduce the heat. Any liquids or gas applied directly to machining operation to improve cutting performances. There are two main problems. Number one is heat generation at shear zone and friction zone. Number two, friction at the tool chips and tool work interfaces. Wash away, some of the benefits also, apart from heat reduction and friction reduction, some kinds are wash away the chips. It can move the chips into the some channels, reduce temperature of the work part for easiest handling, and improve the dimensional stability of work part. This may be stability of the dimension because as temperature didn't rise, so that thickness remains the same. I'm sorry. Cutting fluid functions can be classified according to these are fluids. Fluids can be classified according to the function. Number one is coolants. These are designed to reduce effect of heat in the machining, but lubricants designed to reduce tool chip and tool work friction. Coolants. What are used as base in coolant type? Coolant cutting fluids most effective at high cutting speeds where heat generation is high and high temperature is our problems. Most effective on tool material that are most susceptible to temperature failures, e.g. at high speed steels. Lubricants use the oil-based fluids most effective at lower cutting speeds, also reduce temperature in the operation. Cutting fluid contamination includes tramp oil, that may be machine oil, hydraulic fluid, etc. Garbage, secret birds, foods, small chips, and molds, fungi, and bacteria are the contaminants of the cutting fluid. Dealing with cutting fluid contaminants, these are some contaminations and how to deal with these contaminations. Replaces cutting fluid at regular and frequent intervals. Use filtration system to continuously and periodically clean the fluid. Dry machining. Cutting fluid filtration may be, what are the advantages? The advantages include prolong cutting fluid life between changes, reduce fluid disposal cost, cleaner fluid, reduce health hazards, low machine tool maintenance, longer tool life. And dry machining is the factor that no cutting fluid is used. Avoid problems of cutting fluids, contamination, disposable, and filtration. Problems with dry machining are overheating of tool, operation at lower cutting speeds and productions, and absence of chip removal benefits and cutting fluids and grindings and milling. When the lubrications are used, dry machining, this is not dry machining, but when the term dry machining is used, there is no lubrication or less lubrication. So that's all for the cutting tool technology. I hope you liked the lecture. I'm again sorry for my light voice. I hope you will understand the things, and see you later in the next video. Till then, take care.